Okay, let's unpack this. Imagine trying to keep track of a multi-stage project, but every time you blink, your memory resets. That's kind of like traditional serverless functions for those long-running tasks, right?
Yeah.
But what if your serverless functions could not only remember everything, but also pick up exactly where they left off, even after, say, a system restart? Think about the mountains of custom code, the infrastructure you'd normally need for that resilience. Durable functions. They claim to slash that complexity, maybe simplifying things by like 80%. Our deep dive today is all about Azure Durable Functions. It's this powerful extension to Azure Functions that, well, it completely changes the game for these stateful scenarios. Our mission, cut through the complexity. We want to arm you with the core knowledge how they let you build fault-tolerant workflows serverlessly, explore real-world patterns, and nail down the best practices. The goal is you walk away well-informed, ready to think about how this might revolutionize your own projects.
Yeah, and what's really transformative, I think, is how they directly tackle that fundamental challenge. In a stateless world. They introduce what we call stateful serverless. It sounds a bit contradictory, but
Right.
it allows a workflow to span seconds, days, months even, all while you get the usual serverless benefits, scalability, cost efficiency, and the underlying durable task framework. It does all the heavy lifting. State management, checkpointing, automatic restarts. It frees you up. You get to focus purely on your business logic, not the plumbing underneath.
So if I'm building a cloud application, the core problem they're solving, it's that normal serverless functions, they're great for quick, stateless things, event-driven tasks, but they just fall short when your processes need to remember things over time, like complex, multi-step workflows.
Precisely. You need context. You need state. Think, a multi-stage document pipeline, not just firing off one email. And durable functions, they aren't just like an add-on. They're a really significant enhancement to Azure Functions. They empower you to actually author stateful functions, their main purpose. Dramatically simplify building those apps that demand state management, automatic checkpointing, graceful restarts for long processes. It abstracts away so many infrastructure headaches, things that used to be a real pain. So you get kind of the best of both worlds.
Yeah.
Serverless agility and cost, but with the robustness, the memory of a traditional stateful app.
That sounds like, a dream for developers who've wrestled with keeping track of where some long process is. Are we talking true resilience? Like, if the system crashes or I deploy a new version, the process picks up where it left off?
Absolutely. That's honestly one of their standout features. They're designed to be incredibly fault tolerant. Think of it like having this intelligent supervisor for your tasks. It remembers everything, takes diligent notes at every key point. And if anything goes wrong, server crash, network glitch, maybe a redeployment, it just consults those notes. It makes sure the job gets done, picking up exactly from the last known state. It's not just resilience, though. It's about eliminating the need for you to custom code all that retry logic and state persistence yourself. Plus, you get built-in error handling and retry policies, which simplifies things even more.
That's powerful stuff. So, okay, to make this work, it's not just one type of function doing everything, is it? Sounds like we're talking about a whole team of specialized functions working together. Can you break down who does what?
You're spot on. It's really a symphony of functions, a good way to put it. At the heart, right, you have your orchestrator functions. These are the conductors. They define and coordinate the stateful workflows, but they do it in code. They describe the sequence of actions. They're durable, reliable, and their progress gets automatically checkpointed. But here's the critical rule, the really important bit for orchestrators. Strict determinism.
Determinism. Meaning?
They have to produce the exact same result every single time they're replayed. Think of like a chef following a super precise recipe. Every step, every ingredient measurement has to be identical every time. Otherwise, if you stop halfway and restart, your cake won't turn out right, will it? This consistent replay is absolutely vital for correctness. And orchestrators, they're usually kicked off by client functions.
Okay, so the conductor sets the rhythm. Who actually performs the individual tasks then?
That's where your activity functions come in. They're the workers, the specialists. They perform the individual units of work within that orchestration. And unlike orchestrators, they have no determinism constraints. So they can make network calls, do heavy CPU stuff, the actual work. The key recommendation for you, though, is make them idempotent.
Idempotent?
Yeah.
Meaning safe to retry.
Exactly. Because they have an at least once execution guarantee. Things can sometimes run more than once if there's a glitch during acknowledgement. So, making sure they can be safely retried without causing weird side effects like charging a customer twice, that's crucial. Idempotency prevents those headaches. In, say, an order process, checking inventory or charging the customer, classic activity functions.
Got it. Orchestrators conducting activities, doing the heavy lifting. What about managing specific little bits of state, like counters or something?
Yep. And these are particularly clever. Entity functions, I like to think of them as maybe durable actors or state managers. Their main job is to explicitly manage small, persistent pieces of state. We call them durable entities. They define operations for reading and updating that specific data. They have their own unique trigger type, an entity trigger. They're perfect for managing things like counters or aggregators or any kind of mutable state across different function calls. And finally, you have the client functions. These are your initiators.
The ones that start everything.
Right. They kick off orchestrator or entity functions, usually by sending a message to something called a task hub. They also let you interact with orchestrations that are already running. You can query their status, send them events, even terminate them. Basically, any non-orchestrator function that uses a durable client output binding can act as a client. So an HTTP trigger, a timer trigger, an Azure Event Hub trigger. Lots of options.
It's a really well-defined architecture, seems like.
Yeah.
Okay, you mentioned this task hub that client functions send messages to. How does all this magic actually happen under the hood? And, well, is there a catch? Because magic often comes with some fine print, doesn't it?
That's a very astute observation, because while durable functions abstract away a lot of complexity, the real insight for you, the architect or developer, is that this convenience isn't entirely free. Understanding the plumbing is absolutely key to cost optimization and performance tuning. So durable functions leverage Azure storage, specifically queues, tables, and blobs. That's their backbone. It's fundamental to their durability. The task hub you mentioned, it's really just a logical container for all your orchestrations and activities, but it's physically backed by those Azure storage resources. So when a client function starts an orchestration, it writes a message to an internal storage queue. That triggers the orchestrator. Then, whenever an orchestrator hits an await in C# or yield Python JavaScript, the framework automatically checkpoints its progress, its whole execution history, input parameters, local variables, all that state data. It gets stored in Azure storage tables. If anything interrupts the process crash, restart, whatever the orchestrator can reconstruct its exact state by replaying this history from the tables, it resumes precisely where it left off. And for bigger data payloads, that's where Azure storage blobs come in to handle the heavier lifting.
Right, so the magic is basically constant communication with Azure storage, saving its place, like you said, like a diligent reader bookmarking every single page. But you're saying that constant back and forth, all those saves, that's where maybe silent costs or even performance hitches can creep in.
Exactly. That's the trade-off, you know? This constant interaction with Azure storage for checkpoints, for history, it can significantly impact your operational expenses. Storage pricing is based on the volume of logs and the number of operations. Lots of checkpoints mean lots of operations. And for really high throughput scenarios, that constant chatter can sometimes lead to increased latency because you might bump into Azure storage rate limits. So it's definitely not a set and forget solution if you're not watching those aspects.
That's a crucial point.
Yeah, and a key takeaway here is that while Azure Storage is the default and it's robust, it might not always be the optimal choice for every single scenario. But the good news is you're not totally locked in. There are alternative storage providers, things like Netherite or even MS SQL. They offer different performance and cost characteristics. MS SQL, for instance, can even consume external events and update the orchestrator state transactionally. That could be really critical in some cases, maybe to help mitigate duplicate events if that's a concern. So understanding these underlying mechanics, crucial for real cost optimization.
It's fascinating how these different parts work together. It sounds like you can build really sophisticated, almost human-like workflows. Let's talk about some common application patterns. What kind of epics can we actually write with this?
Right. And what's really cool here is the versatility. These aren't just like theoretical ideas. They're genuinely battle-tested patterns. They massively simplify complex distributed application development. Think about orchestrating a multi-stage approval process. Maybe it takes days. Before durable functions, that could be a total nightmare. Custom state machines, database polling, complex retry logic, just messy. Now, often it's just a few clear lines of orchestrator code.
So what are some of these patterns?
Well, a really common one is function chaining. Simple concept. Output of one function feeds directly into the next. Think data processing pipelines. Then there's fan out, fan in. This is powerful. You execute multiple functions in parallel the fan out. Then you wait for all of them to complete and maybe aggregate the results, the fan in. Imagine resizing I don't know, 10,000 images after an upload. This pattern makes that incredibly efficient. And it's achieved pretty easily in code, like with task.wenall in C# or context.taskle in Python.
Okay, this makes sense. What about for things like web apps or even getting humans involved?
Yeah, great questions. For web applications, the async HTTP APIs pattern is a game changer. A client makes an HTTP request to trigger a long-running operation. Instead of waiting and blocking, it immediately gets back a response, usually with status URLs. The client can then pull those URLs to check progress or maybe send events to influence the workflow later. No more blocking users waiting for complex backend stuff. Then you have the monitoring pattern. This is like a flexible, repeating process inside your workflow. It might pull an external system or track some long-running job until specific criteria are met. It uses durable timers to manage the waiting and checking. And the human interaction pattern. This one's really neat. Your code can literally wait for a person to do something.
Wait, really? Like pause execution?
Yes. A workflow pauses and waits for a human response, like an approval click in an email within a defined time limit. You can build in timeouts, too. It's critical for things like approval workflows, maybe multi-factor authentication steps, or scenarios needing manual data entry. And finally, there's the aggregator pattern, which often uses those stateful entities we talked about. An entity function collects and aggregates data from multiple different sources over time, maintaining that persistent state. Super useful for real-time metrics aggregation, processing IoT data streams, or managing persistent counters across lots of different inputs. The point for you is these patterns mean less custom plumbing code for common but often intricate scenarios, more time for your actual business innovation.
Okay, this is definitely where the rubber meets the road. It's not just what you can build, but how you build it reliably, cost-effectively. What about the practicalities for developers day-to-day? Languages, tools?
Yeah, for developers, durable functions are pretty accessible. They generally support most major languages, right? C#, Java, JavaScript, PowerShell, Python, Fshark. You can even use TypeScript via transpilation. A key trend to watch, and honestly, what you should probably prioritize for new projects is this evolution towards the more modern programming models. Things like the .NET Isolated Worker Process or the Python v2 and Node.js v4 models. They give you much greater control over dependencies, over the runtime environment. They generally make life easier. And hey, if your favorite language isn't on that list, custom handlers let you use pretty much any language that can handle HTTP. Think Rust, Go, whatever.
And the tooling. Local development.
Tooling is solid. You've got templates in Visual Studio, VS Code, the Azure portal itself. The Azure Functions core tools are essential for local development and debugging. And there's the Azurite emulator for mimicking Azure storage locally. Plus, of course, a language-specific SDKs Microsoft, Durable Task for .NET, Durable Functions NPM package for Node, Azure Functions Durable on PyPI for Python, and extension bundles help manage dependencies for non.NET languages.
So, okay, how does this translate into actual code? Let's take that document processing example again. Function chaining, right? How would we stitch that together?
Great question. Let's walk through that flow conceptually. You'd start with a client function. Maybe it's triggered by an HTTP request. That function calls something like schedule new orchestration instance async in C# or start new in Python. That kicks off the orchestration. Then your orchestrator function, the conductor, takes over. It sequentially calls its activity functions. First, it might use context.calActivityAsync or context.calActivity in Python for, say, an extract text activity. It waits for that to finish. Then it calls another one, maybe summarize text activity, waits again. And finally, maybe extract key phrase activity. Each await in the C# orchestrator or yield in Python JavaScript, that's the magic point. That's where the framework automatically checkpoints the progress.
Ah, so those await or yield keywords are signals to save the state.
Exactly. It's at those points that the orchestrator's current state gets persisted to Azure storage. That allows it to resume right there if anything interrupts it.
It's impressive how clear that becomes when you map it to the code constructs. But, all this power, there must be pitfalls, right? What are the absolutely critical best practices that you, the listener, really need to keep front of mind for reliability, performance, cost?
Oh, definitely. And connecting this back to the bigger picture, these best practices, they're your safeguards. Ignore them. And you can run into unexpected behavior, performance bottlenecks, maybe even spiraling costs. First off, and we mentioned it, but it's worth hammering home, idempotency for activity functions is critical. Non-negotiable, really. Since activities are, at least once, make sure they can be safely retried without messing things up. No double charging. Second, deterministic orchestrators are paramount. Avoid any non-deterministic APIs directly in your orchestrator code. No datetime. Now, no good context.NuGrid, no random. Instead, use the context objects versions like context.current@datetime and context.NuGrid. They guarantee consistency during replays. For C# developers, the Roslyn analyzer that comes with the SDK is invaluable here. It catches many of these determinism violations right in your editor, saving huge headaches later.
Those small details, yeah, like using context.current_datetime instead of datetime. Now, or making activities idempotent. Yeah, they sound minor, but you're saying they're absolutely critical design points. What else?
Beyond those two big ones, break down your tasks. Use smaller, more focused activity functions. This improves fault tolerance. If one small step fails, it's easier to manage. It helps with monitoring. And it helps manage the individual activity function timeout, which is typically 10 minutes by default. Also, manage input-output size. Sending huge data payloads back and forth between functions increases serialization latency and cost. If you're dealing with big data, store it in blob storage first. Then just pass references like blob URLs or names between your functions. Much more efficient. And obviously, but crucially, avoid sensitive data in your state or logs. Never persist secrets, connection strings, PII directly in the orchestration history or logs. Use things like managed identities for authenticating to external services securely.
Makes sense. Anything else on the operational side? Deployment, cost?
Yeah, a couple more things. Use unique Task Hub names if you happen to be sharing an Azure storage account between multiple durable function apps, except, of course, if you're deliberately geo-distributing the same application, then they should share the name. For cost optimization, beyond just writing efficient code, think about your hosting plan. Consumption is great for spiky, intermittent workloads, but premium or dedicated plans can mitigate cold starts if predictable performance is key. And crucially, monitor your associated service costs. Don't just look at function execution time. Azure Storage and Application Insights can become significant cost drivers under heavy load. Keep an eye on those. Monitoring tools are your friend here. Application Insights gives detailed logging and tracing. The Azure Function App Diagnostics can help troubleshoot. And that Durable Functions Monitor extension for VS Code, it gives a great visual representation of your workflows, really helpful for debugging.
So it's clear it's not a one-size-fits-all silver bullet, but definitely a powerful tool. It fills a very specific, very important gap in the serverless toolbox. It really is about choosing the right tool for the right job and knowing when durable functions are your best bet. How do they stack up against other Azure services people might consider? Or even options in other clouds?
That's a crucial decision point, absolutely. When you're faced with a complex problem, how do you decide which Azure service is the optimal fit? The key is understanding the primary focus of each service. What's its core strength? Let's take Durable Functions versus Azure Logic Apps. Durable Functions are code-centric. High control, lots of flexibility. You write in C#, Python, JavaScript, etc. Ideal for complex, custom business logic, advanced programming needs, those long-running stateful processes where you need fine-grained error handling. Logic apps, on the other hand, low code-on-code. Visual designer. They excel at integrating different services using pre-built connectors, preferred for simpler workflows that are heavy on integration, business process automation where you don't need deep custom code.
But they can work together.
Oh yeah, beautifully. They often synergize. You might have a logic app handling an external trigger and some initial data mapping, which then calls a durable function to execute some really complex, stateful business logic. Or vice versa.
Okay. And what about compare them to something like Azure Service Bus? Isn't that for reliable processing too?
Good question. But they serve different primary purposes. Azure Service Bus is fundamentally an enterprise message broker. Its focus is reliable, decoupled, asynchronous messaging between different applications or services. It ensures messages get delivered reliably. Durable functions, while they use messaging internally, usually via those Azure storage queues we talked about, their primary focus is stateful orchestration of workflows, managing the internal state, the checkpoints, the restarts within that workflow. So they're complementary. A durable function might send a message to Service Bus to notify another system when a step is complete, or a message arriving on Service Bus could trigger the start of a durable function orchestration.
Right, different layers of the problem. And for really big compute jobs, like rendering farms or something.
Yeah, for that kind of thing, Azure Batch is usually the better fit. It's designed specifically for large-scale, highly parallelizable, compute-intensive tasks. Think massive image rendering, scientific simulations, things needing significant dedicated compute resources. Durable functions are much more cost-effective for workloads that are more intermittent, sporadic, but still stateful. Because they can efficiently pause and resume, they only consume compute resources when they're actively doing something. For those kinds of bursty stateful jobs, durable functions could potentially be, say, 3 or 4 times cheaper than keeping batch nodes running.
Okay, and looking quickly across the cloud landscape, AWS Step Functions often comes up in comparison.
It does. Both provide stateful workflow orchestration in a serverless context. They solve similar problems. The main architectural difference really lies in the authoring experience. Durable functions, as we've discussed, use a code-first, imperative approach. You define your workflow logic directly in C#, Python, whatever. AWS Step Functions uses a declarative approach. You define your workflow as a state machine using JSON or YAML. The choice often comes down to team preference. Do you prefer expressing logic directly in code or defining it visually or declaratively in a state machine definition? Some people find durable functions feel a bit more natural for complex orchestration logic and state manipulation directly within their familiar programming language.
This deep dive has really illuminated how Azure Durable Functions truly elevate serverless computing. They let us build applications that aren't just agile, but also incredibly resilient and, well, smart. They definitely seem like a robust, scalable, reliable solution for building those complex, long-running, stateful workflows serverlessly. Abstracting away so much of that state management complexity is huge. So key takeaways for you, the listener. Remember the critical importance of deterministic orchestrators and idempotent activities. Be mindful of those underlying storage costs and potential performance impacts. And definitely leverage the powerful monitoring tools available. It's about that holistic approach, design, coding, operations for real success. It's been a fantastic shortcut to getting well-informed about what feels like a truly game-changing technology.
Absolutely. And maybe a final thought to leave you with. As these serverless frameworks and durable functions continue to evolve, as they start handling increasingly complex, truly mission-critical business processes, what new demands for things like observability, maybe governance, do you think will become paramount? And how might a service like durable functions need to adapt in the future to meet those emergent needs? Something to chew on.